So we saw from the previous video that 6 low-numbered fractions produced or generated 6 consonant notes from the bottom note C, and then we added in 5 dissonant notes to form a scale of 12 notes plus the C at the top. What we really want is to be able to have these notes evenly spaced, and the reason for that is so that when we change the key of a song it doesn't sound out of tune. This is the idea of equal temperament and is what most keyboards and other musical instruments are tuned to today. So what do we mean by changing the key of a song? Well, the key of our song was in the key of C because it starts on the note C. Well, that's fine, but what happens if our singer can't sing that low? If she starts from the note D dash and sings the same song, it will be in the key of D dash. Now that's fine, but there is a problem. Now 1.5 times the frequency of the note D dash is not the same as the frequency of A dash. This is the problem of just intonation. The frequencies just don't work out correctly. We need a way of splitting up the keyboard equally such that the notes are equal tempered. They're all evenly spaced. So how many notes or intervals do we split the octave up into? Well, we saw how the ratio of 3/2 when using the just intonation produced the note G dash, and this seemed quite an important ratio. It's quite a nice one using a nice low numbered ratio. So let's try and see whether we can find a note on the equal tempered scale which coincides with that 3/2 or 1.5 times frequency. So let's split our octave up into 6 equal divisions. Now here you can see that that's all well and good. The notes are nicely evenly spaced, so we won't have a problem changing the key of the song. But the problem here is that there's no note anywhere near this nice ratio of 1.5 which generated G dash. It'd be nice if we could incorporate some or all of those consonant note ratios. So what happens if we increase the number of notes to 9? Well, there is a note on the equal tempered scale here that is approaching this 3/2 ratio of G dash on the just intonation scale. It'd be nice if we could get even closer though. So what happens if we increase the number of notes from 9 to, surprise surprise, 12? Here we have a note on the equal tempered scale which is pretty much exactly on the 3/2 line. So wouldn't it be good if we could incorporate not just one note, G dash, but as many of the consonant notes as possible into this new equal tempered scale? Well, let me superimpose the 6 consonant notes onto this equal tempered scale and see how far out they are. Now here you can see that, as we already know, the 1.5 G dash frequency is pretty much spot on, and so is the F dash, the 4/3 frequency, and the others are not quite so good. But you will find that this 12 note equal tempered scale is actually the best match. You can go up and have far more notes in your octave, like 40 or so, and get a better match, but who wants 40 notes in their octave? It's just impractical. So you find that a 12 note equal tempered scale is the smallest equal tempered scale that contains all 7 of the basic consonant notes, and remember it's these 6 plus the C which is consonant with itself. So now we've got the best of both worlds. We can now change the key of our song and it won't sound out of tune, and we can also incorporate notes which have frequency ratios which sound good together. So using a compromise between these two systems, we find that 12 notes is the ideal number of notes in your scale. So we have an equal tempered scale, here shown in blue, that has the lowest number of equally spaced notes, 12, that incorporates the 7 consonant notes, here shown in green, to within 1% of frequency, and there are more consonant notes, 7, than dissonant notes, 5. And that is why we have 12 notes in our octave.